So even though we're jumping into this discussion on arc length, the first thing I want to do is I want to recap this discussion that we had. Actually, it was the very last thing we talked about in class before the exam, and that was that if you have a curve that has a constant magnitude, then when you dot that with its velocity, it's always orthogonal to its velocity vector. So its position vector will always be orthogonal to its velocity vector if it has a constant magnitude. Okay? That's going to be exceptionally important today because we're going to be looking at a lot of unit vectors, and unit vectors by definition have a constant magnitude of 1. So we're going to need this result today. So you can take a look at it. The proof is here. I think we talked through it in class briefly. I think I did it off to the side when I did it. But the proof hinges on, first of all, being able to calculate the derivative of a dot product of two vectors, and then just simply rearranging, and then remembering on the right-hand side, we're taking the derivative of a constant, and the derivative of constant 0. And eventually we get down to a statement that says, if r has a constant magnitude, so you've got a vector valued function with constant magnitude, then when you dot it with its derivative, the result will always be 0, and the geometric interpretation of that is that the vector and its the vector function and its tangent vector are always orthogonal to one another. So we're going to need that later on today, so I just wanted to highlight that since it was right above where we're starting off. So what I want to do now is I want to do a quick look at arc length. I'm not going to spend a whole lot of time formally developing the arc length, the formula for arc length. You've seen it done a few times, and I went ahead and made a video for you that you can watch if you want to see that. But I just want to kind of get to the highlights of it. So if we had some vector valued function here, say r, if we plug in a value time, let's go ahead and put, we'll just put in t naught here. And then we think of letting a little bit of time pass. So we're going to let an increment of delta t pass here. And that'll give us another vector along this function, which I'll go ahead and denote as r of t naught plus delta t. Okay. And so, and let me just say this, our goal is to come up with the length of this curve. And so our strategy is to look at, first of all, this difference right here. Make sure I've got that handy. That difference right there, and I'm going to call that difference. Now let me be a little careful here. I'm going to go ahead and draw the difference along the curve, which is this curve segment right here. That's our delta s. Okay. And so what we see then is that delta s is approximately the and so. Rather than thinking of delta, I do need to say this, rather than thinking of s as a vector here, we're not talking about s as a vector here, I want to talk about it as the length along this curve. Okay, so that's important. I'm not talking about the vector that's formed from the difference of these two vectors. I want to talk about the length along this curve. And so that's some sort of, that's some sort of scalar value. And so rather than trying to compute delta s, what we are going to think about is the difference between r of t naught plus delta t and r of t, and that's a vector. So my goal is to come up with an approximation for what I drew in blue there, but we're going to approximate it with that red vector, but what? Well, I'm saying that delta s is supposed to be a length, and so what do I need to do with that red vector there? I need to take its what?
Magnitude.
We've got to take its magnitude. Good. So we would take the magnitude of the difference between these two vectors. Let me draw it a little smaller. We're going to take the difference of the magnitude of those two vectors. So there we've got r of t naught plus delta t minus r of t naught. Okay. And that's going to give us the length of the red arrow there, which I'm arguing is, and I'm using that symbol there for approximately, is approximately the length of that blue curve segment. Okay. So on both sides we have a scalar, so one thing we could go ahead and do is we could divide both sides by delta t. Okay. and then bring that delta t inside the absolute value. And so we end up with, let me go ahead and just extend the absolute value lines like this. Yeah. And so we've got a ratio of how a small change along the, looking at a small change in the length along the curve given a small change in unit time. Okay. And kind of waving my hands at the argument, we're going to go ahead and then say, well, as that delta t gets closer and closer to 0, the difference between the difference between the length of the red arrow and the blue segment of curve that we're trying to approximate becomes smaller and smaller. And I've tried to kind of accentuate that by showing you I've zoomed in on the curve here, and you see the further and further we zoom in on the curve, as you saw in Calc 1, the closer that curve seems to resemble a line, and so the better the blue segment and the red segment align with one another. Okay. So just sort of waving our hands at it, we're going to say that if we took ds dt, that this is equal to the limit as our delta t goes to 0 of the absolute value of r of t plus delta t minus r of t. And here I've dropped off the t naught because this will hold for, this was just for one instance in time, but we can actually think of this as the r of t vector value function over delta t. But this is simply the magnitude of our derivative of our position function. Okay. By the way, I think there's a really helpful way to think about all of this, and that's to go ahead and write that ds is equal to the absolute value of, or the magnitude of, the derivative of our position function times differential t. So I think this is a really helpful little mnemonic to remember, and I'm going to refer to it a couple of times in the notes. And if you'd like more of a description, I highly encourage you to watch the video that I reference here, and I'll point out where the link is for that. But I just want to show you that we could think of differential s as a small change in distance along the curve. Okay? So we could think of differential s as a distance. And how could we think of the magnitude of our position vector? What's one interpretation of that? The magnitude of the derivative of our position vector. What's one interpretation of that?
The direction that the function is going at that point.
Let's actually be careful here. If I'm taking magnitude, we're talking the length of the tangent vector.
Well, the speed at which it is moving.
Yeah. So this is the speed, and then times a small unit of time. Okay? Or if you think about how you said this in an algebra class, you sometimes call a speed a rate. And so I think this gives you a really nice little mnemonic for remembering everything. Distance is equal to rate times time. And I wanted to show you that because that's the aspect that's a little bit different when we work with a parameterized curve when we talk about arc length, as opposed to maybe some of the other ways you considered it in other classes. Is that there's an element of speed as we move along this curve here that we want to capture. And this way of writing ds dt shows that component of speed inside of this integral. So, long story short, let's suppose we've got a vector valued function, and here I'm just doing this for the case where r is equal to 3. So it's got these three component functions, f, g, and h. Okay? And we've got it's parameterized, forms a curve, and I add that f, g, and h are all smooth. Okay, what was the definition of smooth? We're going to have to refer to that a couple times today. So you want to remember the definition of smooth?
Does not have a cusp and is continuous.
Yeah.
Okay. So does not have a cusp. That's true. That's one thing that we're going to capture when we do this.
Like mathematically, for every point on that segment, you can find the limit at every point.
Okay.
And then you can it's also defined at that point. And
okay.
The limit at that point equals the evaluation at that point.
All right, so Dustin just gave the definition of continuity. Okay, and I agree with that a smooth curve is certainly going to be continuous, but I don't think continuous is enough to be a smooth curve. Okay?
If there is a cusp at one point, the derivative will be undefined, right?
Okay, so if we don't want to have a cusp, we certainly need the function to be differentiable. So we'll say the function is smooth. Yeah, so
saying it's continuous already means that there's no cusp.
ooh, careful, not at all, right? So for a continuous curve here, that's a good guess, but for a continuous curve like this one right here, what's the limit as x approaches a?
0.
Of this function here, it would be 0. And what would be f of a on this graph? It would be 0. They agree with each other. So we are continuous where we have a cusp.
Okay.
So let me just go ahead and give the answer, folks, because I'm not hearing it. To be smooth, you first of all have to be differentiable, which means the derivative exists there. And so a consequence of saying it's differentiable is that it's continuous, but being continuous isn't enough to be differentiable. Okay. So it's got to be differentiable. So you have to be able to take the derivatives of f, g, and h. But that's actually not enough to be smooth by the way we defined it. We also said that the derivatives couldn't be what?
Equal to 0.
Zero vector?
Exactly. So we said that this curve, yeah, so let's do it in the context of the curve. For this curve, r of t, this curve is smooth if all of the component functions are differentiable and the derivative, or let's just say another way, the curve is smooth if it's differentiable and the derivative is never 0. So anyway, keep that in mind that when we say smooth, we mean that this r of t is differentiable, but we also mean that r of t never equals 0. And we need that for most of the stuff that we're doing in this class, for most of the things we're doing in this section. Okay?
Also, where's this set of notes? Because week 5 is empty for me.
Yeah. So Cedric, if you go under, so we're finishing up the 14.3 notes, which we started here at the very end of week 3.
Oh, it's in 3. Okay.
So if you go there, there's the 14.4 notes, and then also we'll be referencing the 14.5 notes as well today. Yeah.
Okay.
Great. Good question. Thank you. Okay, so then let's suppose that r of a gives us a tip at point P, and r of b gives us a tip at point Q. Then the arc length between the points P and Q, so L is going to be the arc length between the points P and Q, so we could say that's the integral between P and Q of just differential S, but that's not although it's a very nice way of writing the arc length, that's not a very useful formula for it. Okay? So that's equal to the integral from t equals A to t equals B of the what? Well, so let's just reiterate what we did here. We found the length of this little red arrow here, and what do we want to do? That gave us the length of, approximately the length of one little segment of curve, and we want to add them all up. And so what tool does that for us? The integral adds those all up for us. So we're going to be adding up all of these segments of little lengths of tangent vectors, so r prime of t dt. And why do I have to put the absolute values there? Because I'm adding up the lengths of all of these tangent vectors. Okay? And again, there's a nice little mnemonic, I think, for remembering it. So I'm going to say it one more time. That is that the length, the distance, is equal to adding up a bunch of increments of rate times time. And remember, we learned in an earlier class, we could think of distance as rate times time. Okay? So this is a perfectly fine way to leave the arc length. This way of leaving the arc length formula, although it's nice, isn't very useful. This is a perfectly good way of leaving the arc length formula. Okay? But if we want to think about that in terms of the component functions, this will be the integral from a to b of, well, how do we take the magnitude? It's the square root of each of the components squared, the sum of each of the components squared. So the square root of, and now careful, we're not talking about r, we're talking about r prime here. So that's f prime of t quantity squared. Let me write that a little more carefully. F prime of t quantity squared plus g prime of t quantity squared plus h prime of t quantity squared. Okay. And folks, even just with how messy writing that out got, just because I didn't give myself a lot of room there, I do want to say that one of the hard things about this class is sometimes switching back and forth between convenient notation, something like this or something like this, and switching to a more practical notation of something like this. It's easy to, when you look at a long expression like this, where we've given all the particulars, to kind of get lost in the process. So one thing you're going to want to practice doing in this class is swapping back and forth between these three different viewpoints of the ways we can represent arc length. Okay? So by the way, I did this all for 3 space. You could redo the same thing for 2 space. You would only have 2 component functions. Or you could do it for n space, right? There's the formula for arc length is the same in higher dimensions. Just you'd have more component functions. Great. So folks, this is where in number 10 here I say, hey, you've probably seen arc length defined a couple of times. So here's a quick video that just looks at sort of the different viewpoints you've seen over the years of arc length. So if you get a chance, I recommend that you take a look at that. Okay, so let's actually put this into practice here. Okay? And here's a nice concrete example that I took from the text, where we've got an eagle that's flying in flying in a elliptical path. Okay, so it's circling around, but as it circles, it's rising upwards in this case. Okay? And it's rising upwards at 100 vertical feet per minute, and that's reflected by the z component there that tells us how our, if we think of this as, north, south, east, west, and horizontal, that tells us how our horizontal component is changing. And in fact, just to remind you of the elliptical path, we would start here when time is 0. We're at the order pairs. So x is 0, or x is 1. X is 250. Excuse me, the length of that 250. Y is 0, and z is 0. And then we begin spiraling up in this elliptical path like this. And so, if you were to look down the z-axis, what would this path look like? If you look down the z-axis.
It would just look like a circle.
It would look like a circle. From above, it would just look like the eagle's just flying in a circle with radius what, folks?
50.
Okay, so what's the radius of this, folks? So remember, the radius simply, so this would describe a radius, a circle with, so if you put this into x and y form, I can't remember who said 50. Phoebe, maybe it was Phoebe. Was that you? I'm not sure who said 50.
No, that wasn't me.
Okay. So if you were to put this in, the form x squared plus y squared equals r squared, you would go ahead and square the radius. But remember, when we're in this parameterized form, think of it this way. When t is 0, we go out 250 units in the x direction. And say when t was pi, we would go backwards 250 units in the x direction. So the radius is just 250 here. Great. Okay. So here's the question. Time is measured in minutes, and the output is measured in feet. So how far does this eagle travel during 10 minutes of flight? Okay. So this is really going to be kind of a plug and chug of that arc length formula. So the path that the eagle flies as flight length is going to be the integral from t equals 0 to t equals 10 of the square root of the sum of the component functions squared. Oops, sorry, what do we have to first compute, folks? Sorry, this is, in fact, let's go ahead and write it this way. This is of R1 prime of t in magnitude dt. So what do we need to compute first, folks?
So we should find r prime.
First thing we got to do is find r prime. And what is our r prime here, folks? So the derivative of the cosine is the
Negative sign.
Great. And then we get 250 cosine of t, and the derivative of the third component is
Just 100.
100. Okay, so now we can go ahead and compute the magnitude of this. So we take the square root of the sum of the component functions squared. So we get the square root of 250 quantity squared plus 100 squared. And let's compute that real quick. Oops. So when I computed that, I got the, inside the radical, I got 72500, taking the square root of that. Well, let's go ahead and just leave it as an exact form for the time being. Okay.
Oh, so you combine sine squared.
Oh, yeah, I'm sorry. I did that a little bit fast, folks. By the way, you're going to notice that a lot of the examples over the next two sections have helixes in them. And one of the reasons why is because you can often clean things up quite a bit using that identity. So yeah, Dustin is exactly correct. I went ahead and factored out the 250 from the first two terms, the 250 squared from the first two terms, and then combined sine squared plus cosine squared to give us 1. Sorry, I did that without commenting about it. Great. Okay. So we can now go ahead and take another look at our arc length and say then that that is equal to the integral from 0 to 10 of the square root of 72500 dt.
Simplified, that's 50 root 29, but I don't know if that's much more helpful.
No, and in fact, we'll go ahead and just get a decimal approximation of this this total length here. But yeah, so when we take the integral, notice we're just taking the integral of a constant in this case. That's really nice. So that's the square root of 72500 times t evaluated from 0 to 10. So we end up with 10 times the square root of 72500. And if we crunch that, what do we get, folks? Let's get a decimal approximation on that. So rounded to the nearest foot, I get 2,693 feet. Okay, oh good, and that's what I listed down there below. Okay, so folks, you are going to have to do, just for practice, some basic, I call these almost plug and chug problems at this point, where we know how to compute the arc length given this arc length formula. Okay, how do you remember the arc length formula? I think of adding up a bunch of little rates times little intervals of time. That's going to be adding up a bunch of little distances. That's going to give you the arc length. Okay. So you're going to have to do some practicing with that, and you'll get some exercise with that in the My Math Labs. Okay. What I went ahead and did was repeated the problem here in number 13, and notice what I did here. I went ahead, it looks like this t cut off a little bit. This should be t for the end of that function. I went ahead and reparameterized this helix. Okay. So just to convince you that this is the same helix, let's just check a couple of things. First of all, if you were to look down the z-axis on this, you would see that it looks like this eagle's flying in a circle again. Again, of what radius, folks?
250.
250. Okay. And notice, just to kind of convince you that we traverse the same amount of that helix. In the first example, how high did the eagle fly? Not how far did he fly. That's the 2693. That's the arc length that we computed. But how high did the eagle fly over a period of 10 minutes?
1,000 feet.
1,000 feet, right? And how high does the eagle fly in this one? Also 1,000 feet. And you could do some work to show that these two are, I mean, we're not going to do the work right now, but to show that these are two different parameterizations of the same curve. Okay? And notice that the key difference here is that this eagle flies the entire curve length in 5 minutes, whereas the first eagle did it in 10 minutes. So they're doing the exact same path, but one is doing it in half the time. Okay? So if I were to ask you, before we even compute this, folks, if I were to ask you, how far did this second eagle fly, what's the answer?
2,693 feet.
The second eagle flies the exact same distance, right? Okay, so that's just two different parameterizations of the same curve, but if I ask the question, how long was that curve, we get the same answer. Okay? And so if you computed this, I just like to finish this part out. So I went ahead and found the derivative of the second function, and then I took the magnitude, or I said to take the magnitude here. Here I've actually computed the magnitude. And then if we just finish the very last step of integration, which is the easiest part of this, let's just finish that out. That's the square root of 290,000 t evaluated between t equals 0 and t equals 5. And if you compute this, you also get the same 2,693 feet that this eagle travels in a time period of 5 minutes. Okay? Okay. So, in the previous two examples, we saw two different parameterizations over two different intervals. And we're getting ready to talk about a topic called the arc length parameterization here. That's what I'm kind of getting ready for. Okay. And the question that we want to ask is there a way we could parameterize this curve so that now careful, this is the time increment, right? In the first case, the time increment went from, this was on 0 to 10. In the second case, the time increment was on 0 to 5. And so I'm asking you, is there a time increment where the length of the time increment is the same as the length of the curve? By the way, this would be an eagle that would take 2,693 minutes to fly 2,693 feet, right? So what's the speed of that eagle?
1 foot per 1 foot per minute.
1 foot per minute would be the speed. That's a very slow eagle, but that's what we're looking for, folks, is a way to reparameterize the curve so that the length of the curve is equivalent to the interval of time over which we're integrating it. And that I would say at first that might seem like a kind of a strange thing to want to do. I'll say first of all, it does allow problems to be computed easier if you already know it has the arc length parameterization. And we're also going to see that it's very important in the next section when we get into talking about the unit tangent and the unit normal vectors as well. And then the binormal is also going to be unit. But having this arc length parameterization greatly simplifies the way we have to represent things. Okay? So that is, we're asking for, can we find a parameterization on this curve so that, and what did I want here? I don't remember what I wanted in this blank. So that when we go to calculate the arc length, we get the integral from just a to b of the absolute value of, or the magnitude of r prime of t dt. But real quick, folks, if this is going to take 2,693 minutes, we just said that this component right here, the speed part of this, has to be what?
1.
Has to be 1. And I'm going to say that on the next page, but since we've already said it, let's go ahead and say it now. So that's going to be the integral from a to b of just 1 dt, which is equal to t evaluated from a to b, which is just equal to b minus a. Okay. So if this were the case, we would say that this curve here has what we call the arc length parameterization. Let me just say that, I'm going to say that formally on the next page. Okay. So if the speed of the parameterization is 1 unit distance per 1 unit time, and notice that time is sort of, it's like we're kind of putting our own units on time, I guess, to force it so that we travel 1 unit of distance per 1 unit of time, then the parameterization is called the arc length parameterization. Okay? Said that, if I say that another way, let's say it like this. If the magnitude of the velocity function of the curve is equal to 1, that simply applies that the integral from a to b of the absolute value, or the magnitude of v, our speed, dt, is equal to just b minus a. Okay? And when you have that, we're going to say that you have the arc length parameterization. So we've seen that there are many different parameterizations of a curve, but what we often want to find is something called the arc length parameterization. And I'm using the word the there to point out that it is in a way unique, but I will say it's only unique up to a choice of constant. Similar to the way we talk about antiderivatives, I guess. Antiderivatives are unique up to a choice of constant. Okay. Okay. So let's go ahead and answer this question here. Does this curve, r of t equals, and then each of the component functions are just e to the t, have the arc length parameterization? And if not, what we're going to do is we're going to go ahead and reparameterize it so it does have the arc length parameterization. Okay? So one way to say that is, if the length of this curve is more than, or if we find out that the length of this curve is more than 4, we've traversed it too fast. And we want to slow down the rate at which we traverse it. And if we find out that the length of this curve is less than 4, then we've traversed it too quickly, and we need to, maybe I said that back, so let me say that one more time. If the length of the curve is more than 4, then we haven't traversed it fast enough, and we need to speed it up. And if the length of the curve is less than 4, then we've traversed it too quickly, and we need to slow down the rate at which we move across the curve in order to ensure that we have the arc length parameterization. So the phrase is we're going to reparameterize it so that it has the arc length as a parameter. Okay? So one thing we could do, folks, is we could go ahead and compute. You could compute the integral from 1 to 5 of the absolute, or the magnitude of our, or the speed of our position function, and then check to see if the answer is 4. If so, we're done. It has the arc length parameterization. And we're done. But that would involve completely calculating this integral, completely calculating this arc length. Okay. But is there a quicker way to see whether or not this has, that's kind of a pun, quicker way to see whether or not this has the arc length parameterization? Rather than completely computing this integral, what could we do?
Can you just scroll up to 16 for just 1 second?
Yeah.
Thank you.
So what's a better way than actually fully computing this integral to check to see whether or not it has the arc length parameterization?
Finding the magnitude of the derivative?
Simply finding the magnitude of the derivative and checking to see if it's what, folks?
Constant.
Not just constant, Dustin, but what in this case?
1.
1.
Checking to see if it has magnitude 1. That means checking to see if this moves at a rate of, and Dustin's right, so we should say that it's a constant rate, but it moves at 1 unit distance per unit time. However, we've parameterized time on this problem. So a better way is simply to check, is the absolute value, or is the magnitude of the velocity function equal to 1? Okay. Now, notice that excludes a whole lot of functions, right? We've seen plenty of functions where the velocity changes with time and the magnitude as well, which is a component of the velocity, changes with time. So what we're saying here is Dustin was exactly correct in that we want to check to see whether or not the magnitude is a constant, but more than that, we want to check to see whether that constant is 1. So let's go ahead and check this. If we go ahead and compute the derivative, our velocity function, so let me start using v here instead of r prime. So if we compute our velocity function, well, that's just e to the t, e to the t, e to the t. And if we go to compute the magnitude of that, that's the square root of e to the t squared plus e to the t squared plus e to the t squared. So that gives us a sum in there of 3e to the 2t's, which simplifies to be the square root of 3e to the t. More specifically, this is not equal to what always?
1.
1 for all t in our interval from 1 to 5. It's probably equal to 1 at let's see, if we plug in a 1 there, we get e. No, it's actually never equal to 1, but even if it were equal to 1 at least one point in time, that's not good enough. It's got to be equal to 1 for all points in time over that interval. Okay? So certainly this does not have the arc length parameterization. Okay, so what do we need to do? Well, we were told that if it doesn't, find a parameterization that does have arc length as a parameter. Okay? So you're going to have to do this a few times. I'm going to do it once now, and I'm not going to make a whole lot of comment on it, and then I'll comment it on a little bit more in a couple more examples. Okay? So one way I think that was easiest to kind of put all these pieces together is we're going to now reparameterize this. We usually, and by the way, I should have said this, when we have something that's parameterized with the arc length parameter, instead of writing t for time, we write s for arc length parameter. You should still think of s as sort of like a unit of time, I guess, but it's the arc length parameterization on it that forces us to move 1 unit distance per every 1 unit time. Okay? So in 1 unit of time, we move 1 unit along the curve. Okay? So remember that the speed could be thought of as just simply ds dt. That is, the magnitude of the velocity function is ds dt, or as I gave you the formula before, I said that I think it's helpful to remember ds is equal to the magnitude of our velocity function times dt. Okay. So what I'd like to do is solve this for the arc length parameterization. And it may be helpful if you're not seeing it, think of there as being an understood 1 there. We'll do it like that. We'll just point there and say understood 1. Okay. So if I were to integrate both sides, or if I were to take the not integrate, let's say take the antiderivative of both sides, this is what I would have. Or put another way, we have that s is equal to, and in our case, let's go ahead and put what our speed was. Our speed was the square root of 3 e to the t integrated with respect to time, dt. So we get just the square root of e to the square root of 3 times e to the t. And folks, this is where you're going to get into trouble on a couple of my math lab questions in here. So I just want to point it out. What do I have to put if I'm finding an antiderivative here?
A constant.
Plus c. Exactly. Now, normally I think the best choice for c is what? What would you normally want to pick for c?
0.
You would normally want to pick c is equal to 0. Okay? And I'm going to go ahead and keep doing that, but I'm going to say that for a couple of my math lab problems, they actually want you to pick something other than 0 for your constant there. So I think, Kazar, a little while ago, you asked me a question about this, and this is where your answer then ended up differing from my math lab answer, was because they ended up picking something like 13 for your constant. Okay? So normally what you would then do is, let me just say this, normally you would solve this expression. So we pick c equals to 0, so we have s equals the square root of 3 e to the t. You'd solve this for t. But notice in this case, I'm not going to solve for t, I'm going to solve for e to the t, because what I'd like to do is replace the expression e to the t here with some expression involving s. So I'm just going to solve for e to the t. Okay. If you don't see why that's beneficial, just go ahead and solve for t. You'd have to take a natural log, and then in place of t, you would plug an expression with a natural log in it, but when you take e to the natural log of something, you're just going to be back to what the argument was. Okay. So instead, I'm just going to solve for e to the t here, so I get that s over the square root of 3 is equal to e to the t, and now I'm going to take my curve, and instead of putting r of t, I'm parameterizing it by the arc length parameterization here. I've chosen an expression s over the square root of 3 so that the speed then is 1. Okay? So I'm going to replace each of my e to the t's in this expression with s over the square root of 3. Okay. And again, if you had fully solved this for t, you would have just said that t is equal to the natural log of s over the square root of 3, but then you'd be kind of repeating yourself. Because then you'd replace t with that natural log expression, but then that goes inside of the exponential function. Okay. Now, we've just had the effect of, my guess is we've just had the effect of slowing down our curve by quite a bit. Okay. So this curve was traveling too fast. We've just slowed it down. So now for every 1 increment of time, we're going to go 1 unit of distance. Okay. But what we also need to do is now adjust the limits of integration here. Okay, or adjust when we're considering time to start and time to stop on this. Okay. So what did time originally start here? When t was what? What was our lowest limit here? When t was 1, we would have that s is equal to what, folks?
E.
Root 3e. Does everyone see that? Probably the easiest place to see it is to go back up here, where I've already got the expression solved for s. Okay. So when t is 1, s is equal to the square root of 3e. And when t is, what was the upper limit? When t was 5, that's when we stopped running this curve. When t was 5, what is s? S is the square root of 3e to the 5th. Okay? So we're going to take this curve, this newly parameterized curve, and we're going to only consider it on the intervals from the square root of 3e to the square root of 3e to the 5. One thing that's really nice is now if you want to go ahead and compute the arc length, computing the arc length is a cinch. That is, if I said, what's the arc length now? So this is the answer. This was the newly parameterized curve. That's what we were looking for. This, and don't forget, you also need to give the interval of time for which that parameter holds. That's our answer. But look how easy it is, now that we've got the arc length parameterization on this, look how easy it is to compute the arc length. It would be the integral of the square root of 3e to the square root of 3e to the 5th of the magnitude of our speed, but now it's parameterized with s instead of t. And so what did we force this, and you can check this, folks. Take the derivative of this. You've got 1 over square root of 3 for each of the components. Square each of those components and add them up. And you would end up with 3 over 3, or 1. When you take the square root of that, you get 1. So this has this has a speed of, or this has a velocity of magnitude 1. The speed is 1. And so when we integrate it, we just get s evaluated from the square root of 3e to the 5th, square root of 3e. And so what's the length of this curve? It's the square root of 3 times e to the 5th minus e. That's the length of this curve. Notice that the length of this curve, and you can check that, the length of this curve is equal to the length of the s interval. That's what we mean when we say it has the arc length parameterization. Okay. So, why did that come out? I meant to not have that come out for you guys. Well, that's okay because we're kind of short on time anyway, so I'll just show you this one. Let me go off to the side though real quick and just make a quick comment. How do you guys normally parameterize a circle of radius 1?
You would have
Cosine t.
sine t and cosine t. Sine as y and cosine as x, of course.
So normally we parameterize a circle this way, as Dustin was saying, and who else?
Me.
As Dustin and Phoebe were saying, we normally parameterize it this way, as the cosine of t, comma, sine of t. On what? This is really important. If we're parameterizing a circle, we want one loop of a circle, we parameterize on 0 to 2 pi. That is our natural choice. Folks, what is the length of this? What is the length of this interval? The length of this interval is 2 pi. Folks, for the unit circle, what is the arc length of the unit circle? It's simply its circumference, right? The unit circle has radius 1, so what's its circumference? Its arc length or circumference is 2 pi times its radius, so it's 2 pi. Why do we normally parameterize a circle this way? Because it has the arc length parameterization. The length of the interval time is equivalent to the arc length as we traverse it. That's really convenient, right? Because what if I think about this bug that's on here on this parameterization, and what if pi seconds passes by? Where did I end up at on this circle?
-1, 0, or 2 pi around the circle.
So if this happens for, I think I said pi seconds? I forget what time I said, sorry. If it went for pi seconds, it would travel a distance of pi around the curve. Or if if it travels pi over 2 seconds, it would go a distance of pi over 2 around the curve. Do you notice what I'm saying here? Is that the length it's traveled along the curve is always equal to the length of time that's been passing. So could you parameterize a circle other ways? Yes, you could. Here's another parameterization. You could say r of t is equal to the cosine of t cubed, comma, sine of t cubed, and then you'd have to find some new interval. I'm not going to give it because I can't come up with it off the top of my head, but that would still give you a parameterization for a circle, but you'd be traveling too fast to be able to use that arc length parameterization use that parameterization advantageously. So this is still a circle, but your speed is too fast to be able to make use of the arc length parameterization, and things are much more difficult to work with then. Okay. All right, so let's go ahead and do this now, and we'll just take a look at this example. Which parameterization of a circle of radius 3 is the most natural choice? Okay. Meaning I want it to be parameterized by its arc length. Now, folks, what could you use as an answer? You could certainly use as an answer 3 cosine t, 3 sine t as your parameterization. Okay. And in fact, I say here, and in fact, there's many other answers. So, for example, you could do t squared and then adjust your time accordingly. There's many other parameterizations that you could use, all of which would describe this curve of a circle. But what I want to have is I want to pick a parameterization where the length of time that it takes to traverse the circle is what? The length of time it takes to traverse the circle is 6 pi. Why? Because that's the distance around a circle of radius 3. That's the circumference of a circle of radius 3. Okay? So for example, let's just take, I think that if I asked all of you to come up with a parameterization for a circle of radius 3, I think all of you would pick this circle right here, probably. Maybe that's pushing it, but I think you'd all probably pick that. Okay? So then I went ahead and computed the speed of this circle. But the speed isn't what? Or excuse me, the speed of this parameterization, not the circle. The speed of the parameterization. But the speed isn't what?
1.
1. And we can see that because when I actually finish out the finding the arc length, I don't get the distance between my two time values. Okay? So what do? This is, in my opinion, this is the key step to understanding what's going on here. It's this part right here that I want to highlight. Okay? We say that ds is equal to our speed times dt. Okay? And then we go ahead and integrate both sides. Folks, if you notice that you could have just set s equal to 3t, which would be sort of what you would see right here when you did the first integration step. But where you'd get into a little bit of trouble is you wouldn't naturally have that option of a constant there. And the book didn't really do a good job of addressing that constant, which I think is fine. But then the MyMathLab expects you to understand it. Okay? So MyMathLab, this is what I want to say here. MyMathLab always expects you to pick a constant so that the lower limit of time is always at 0. Okay. If that confuses you, I went ahead and made a video of me working through one of these MyMathLab problems where you have to do that, where you have to adjust it. And you might be saying, wait, where did they get that minus 13 in the answer from, or something like that? What they're doing is they're shifting everything down so your time starts at 0 as opposed to starting at 13. Okay? So then what I'm saying here is that any parameterization of this form will work for an interval from c to 6 pi plus c. Or if you like, just go ahead and plug in a 0 for c, because that's, I think, the most natural choice here. So you'd go from 0 to 6 pi. Notice that the length of the time interval is now equal to the arc length. So if pi seconds have passed, you've gone a distance of pi along this curve. Or if 2 seconds have passed, you've gone a distance of 2 along this curve. Okay. All right. Folks, you probably didn't have this part right here that I wrote down in your notes. What I've been trying to do is add in notes that you can click on. So for this one, if you just have the PDF, if it's an Adobe Acrobat Reader, you can click that question mark and it just pulls up those notes. Otherwise, this video will be available soon, so you can just go ahead and get it from the video too. All right, so as I say here, folks, here's a video for some additional practice in reparameterizing a curve and explaining why my math lab does the constant the way it does. The book doesn't address this at all, and I don't think my math lab takes the most natural choice. Okay? So this does correspond to this question in your text, this question in my math lab for section 14.4. And so there's a chance to look at some more. I think that's it. Yes, that's it for the arc length. Okay. Wrong button.